So this is RLC 131, Circuit Analysis 1, and this presentation is on series RLC circuits. Now let's begin by looking at the phase relationships in a series RLC circuit. Now we see a series RLC circuit in Figure 1, and again with series circuits, the current is the same for all components, both in magnitude and time. So the source current equals the capacitive current equals the inductive current equals the resistive current. So in this series circuit, we'll use current as the reference, and this is illustrated in Figure 2. The sine wave that represents the current starts at 0 amps at 0 degrees. Now, in a purely resistive element, there is no lead lag time with respect to the current flow through the resistor and the voltage dropped across the resistor. So, as illustrated in Figure 3, the current and the resistor voltage are in phase with one another. But as we've talked about in previous presentations, voltage leads current by 90 degrees in an inductor. Therefore, the inductor voltage happens 90 degrees before the resistive voltage, as shown in Figure 4. And again, we know that current leads voltage by 90 degrees in a capacitor. Therefore, the capacitor voltage happens 90 degrees after the resistor voltage, as shown in Figure 4. So we look in Figure 5 at the vector diagram for the voltages in this series RLC circuit. And again, the resistor voltage is our reference voltage along with current. And the inductor voltage is at positive 90 degrees, and the capacitor voltage is at negative 90 degrees. And note from the vector diagram in Figure 5 that the inductor voltage and the capacitor voltage are 180 degrees apart. And of course, the resistor voltage is 90 degrees different from both VL and VC. Again, for a series circuit, we know that the source voltage equals the sum of the voltages, in this case VR plus VL plus VC. But again, since VR, VL, and VC do not happen at the same time, we must find the vector sum of these voltages in order to determine the source voltage. So mathematically, the source voltage equals the square root of VR squared plus VL minus VC squared. And the phase angle, again represented with the Greek letter theta, is the angular difference between the resistive voltage and current and the source voltage. And mathematically, the phase angle is the inverse tangent of VL minus VC over VR. And note that this equation will return a negative value for theta if VC is greater than VL. Now, the Figure 6 provides us with the vector diagram for impedance in this series RLC circuit. And again, resistance is the reference for this vector diagram, is placed at 0 degrees on the vector diagram. And X sub L is at positive 90 degrees, X sub C is at negative 90 degrees. So note in the vector diagram that X sub L and X sub C are 180 degrees apart. And conceptually what this means is that when X sub L opposes current, X sub C is pushing current. And of course, when X sub C opposes current, X sub L is pushing current. Now, the total reactance of the circuit, symbolized with X sub T, is simply the difference between X sub L and X sub C. So again, the impedance of this series RLC circuit is the vector sum of R and X sub L and X sub C. Mathematically, impedance equals the square root of R squared plus X sub T squared. And we can determine the phase angle of this series RLC circuit by finding the inverse tangent of X sub T over R, or the inverse tangent of X sub L minus X sub C divided by R. And again, this equation will return a negative value for theta if X sub C is greater than X sub L. Now, figure 7 provides us with the vector diagram of power in this series RLC circuit. And again, resistive power is true power, symbolized as P sub R, and of course this is measured in watts. The inductive power is a reactive power, symbolized with P sub XL, and this is measured in volts amps reactive. The capacitive power, symbolized with P X sub XC, is also measured in volts amps reactive. The apparent power is the vector sum of these powers, symbolized as PAPP, and this is measured in volts amps. Mathematically, the resistive power, the true power, can be calculated with three different formulas: VR times I squared times R, and VR squared divided by R, and the same for the inductive power and the capacitive power. Now, the apparent power can be calculated with V source times I squared times Z, V squared divided by Z, or the vector sum of the true power and the reactive powers. Again, some textbooks use the symbology P sub T for true power and P sub R for reactive power. So be sure you know what the symbology is when discussing the power in these RLC circuits. Now let's look at the analysis of a series RLC circuit. So for the circuit of figure 1, we have a source voltage of 14.14 volts peak at a frequency of 1 kilohertz. And this source is connected to the series combination of a 1 microfarad capacitor, a 100 millihenry inductor, and a 470 ohm resistor. And the first step is to calculate inductive reactance and capacitive reactance. Inductive reactance, 2 pi FL, for the circuit of figure 1 is 628 ohms. Capacitive reactance is 1 over 2 pi FC, and for the circuit of figure 1, this is 159 ohms. So the total reactance, the difference between X sub L and X sub C, is 469 ohms. The total impedance of the circuit is the vector sum of R, X sub L, and X sub C, as shown, and has a value of 664 ohms. The phase angle of the circuit is the inverse tangent of X sub L minus X sub C over R, which gives us a phase angle of 44.9 ohms. And the vector diagram for the impedance of the circuit of figure 1 is shown in figure 8. Now, for the current and voltage calculations, again, I'm using the RMS equivalent of the 14.14 volts peak. So the current in the circuit is V divided by Z, 15.1 milliamps. And the voltage dropped across the resistor is I times R, 7.1 volts. The voltage across the inductor, I times X sub L, is 9.48 volts. And the voltage across the capacitor is I times X sub C, 2.40 volts. Now, just as a check, we find the vector sum of these voltages, the square root of VR squared plus VL minus VC squared, to ensure that we haven't made any math errors in calculating current and or the voltages. And again, we see that we end up with a vector sum of 10 volts, so we feel confident that we have not made any mistakes. Now, the phase angle of the circuit can be calculated using the voltages as shown. Theta equals the inverse tangent of VL minus VC over VR, which gives us an angle of 44.9 degrees. The same value we obtained finding the phase angle using the oppositions to current in the circuit. And of course, the vector diagram for voltage in the circuit of figure 1, or for the circuit of figure 1, is provided in figure 9. Now, the power calculations for the circuit of figure 1 are shown. The true power, VR times I, is 107 milliwatts. The inductor power, VL times I, is 143 millivars. The capacitor power is VC times I, 36.2 millivars. And the apparent power is V source times I, which gives us 151 milliVAs. Now, we can also find the apparent power by finding the vector sum of PR, PXL, and PXC as shown. Now, the power factor for the circuit of figure 1 can be calculated by finding the cosine of theta. The cosine of theta is 44.9 degrees. So the circuit of figure 1 has a power factor of 0.71. And this would be termed a lagging power factor, since the source current lags the source voltage. And of course, the power vector diagram for the circuit of figure 1 is shown in figure 10.